We've been having a wonderful 2 days talk, and this morning we are honored to have Professor Chuck Newman from Courant and NYU Shanghai, where I was born. That's totally unrelated. And Professor Newman is a creative and agile probabilist, according to what I read. And he's made the fundamental contributions to population theory, random networks, spin glass. He's a member of National Academy of Science and American Academy of Arts and Sciences.
Thank you. I'm the organizers for organizing what a very interesting workshop, even for me, more so than I originally expected. And until now, having pretty good weather. I've been coming by bicycle. I made a mistake this morning of thinking the rain had stopped. Well, it had stopped, but then started again. But I brought an extra pair of pants. Right. So this will mostly be a kind of historical review. So that I put down here two review papers, one quite recent, which is a sort of extended version of this talk, which is on the archive, will appear in the Bulletin of the American Math Society. Another one, which is an older one, about, it's in principle related, and it would be very interesting to try to find more relations. It's about connections between Brownian motion and zeta function and xi functions, therefore the Riemann hypothesis. Unfortunately, there don't seem to be any connections so far discovered that relate it to Ising models. And Ising models are, as we know from talks already by Elliott Lieb and David Ruel, the Young theorem is about zeros of partition functions in Ising models, and it would be tremendous to try to figure out some relation, for example, with the Brownian motion connections to the zeta function, but that hasn't been discovered yet. Okay. Right. So I'll get to briefly talk about things related to the Lee and Young theorem later if I don't run out of time. But the first main part of the talk is really about moment generating functions or Laplace transforms and their connection with the Riemann xi function, and that's a very old thing. It goes back to Riemann's original paper. So here's the setup. So we consider a function f. We'll be interested in a very particular function, which I'll write down in a moment. The functions that we'll be dealing with will be functions that are positive and even. So f is positive and will be even. One's interested. Forget this factor with the lambda for a moment. If without that, if f goes to zero fast enough at infinity, then this two-sided Laplace transform will be well defined for complex W, and will be an entire function of complex W. Even if that's not the case for a given f, if you put in this factor with lambda negative, then you will get something which is decreasing fast enough to give you an entire function of complex W. And for some functions f, like the kind that come up in the Riemann hypothesis, you can put even a positive lambda because f decreases at infinity very rapidly. And so anyway, this will be defined for any lambda, any real lambda for which it makes sense, and then it will typically be a entire function of complex W. Sometimes we'll think of the f of u du as because the f is positive, at least if you multiply by the right constant, you can think of, well, even without multiplying by constant, you can think of f du as a Borel measure on the real line, and sometimes you normalize it to make it a probability measure. So that's the general setup. What does this have to do with the Riemann hypothesis? Well, it has to do with a particular choice of f. So there's a specific function, you take f to be the specific function capital phi, which is actually this function of u, of real u. That's the only thing you need to see from this is that for any real u, because this term goes to 0 very rapidly, it's a nicely convergent series, so it's a well-defined real function for real u. And as we'll see in a moment, this function decreases very rapidly. That's for large u. That's kind of obvious for large positive u. It's not so obvious to start with for large negative u, but that is the case. And so even without the little lambda, so this is the Laplace transform, with little lambda being 0, it will be a nice entire function of complex w. So it's that particular choice of phi is important because, as I said, it already appeared in Riemann's 1859 paper. That's one of the formulations of the Riemann hypothesis, and is in terms of Riemann's Xi function, which is actually is up to a multiplicative constant, is this function, this Laplace transform, with little lambda being 0, and except that there's a change of variables, the s of the zeta function, and now when you multiply by these extra factors, that's the Xi function. The critical line for the zeros of the Riemann hypothesis are real part of s equals 1/2. So one just translates that by a half, and then that's the zeros in the w plane are the critical line corresponds to the imaginary axis. So the Riemann hypothesis is equivalent to the statement that this particular Laplace transform of this particular function phi has all its zeros are pure imaginary, are on the critical line, which has now been translated to the imaginary axis. Okay, so now let me make a few comments about this function. Some of them I've already made. So one is that even though it doesn't look like it, this is an even function of u. The evenness of this function phi is the same as the so-called as Riemann's functional equation for the zeta function or the Xi function, which looks a little different because of the change of variables. Because we translated by 1/2, it's simply evenness of the function phi. So that's it doesn't look even, but it is. I'll show you a numerical graph of this function in a moment. So that's, at least numerically, that will verify the three properties I'm about to say. So one is the evenness. Another property is that it's rapidly decreasing. As I said, that's obvious when u is large and positive. It goes to 0 very rapidly, like e to minus an exponential. It's not so clear what happens when u is large and negative, but once you know that phi is even, then it does the same thing for a large negative u. So it's rapidly decreasing. The other property is that this is a positive function of u. So that's elementary for u greater than or equal to 0, because you can just check that these terms here are termed by these, this prefactor is, for each n is non-negative, an elementary exercise. That is not the case when u is negative, but it doesn't matter because since phi is an even function, once you know it's positive for positive u, it's also positive for negative u. So those are three useful properties: very rapidly decreasing, even, and non-negative. Here's what the graph looks like. Done, I think, with Mathematica. This is 0, so you can see that for u bigger than about 0.4, it's practically equal to 0. Of course, it's not 0, but it decreases extremely rapidly, like e to the minus exponential. Other than that, it's not. It's not a very remarkable looking function, and so it's sort of somehow striking that the famous Riemann hypothesis just has to do with the Laplace transform of this particular function. What could be so hard about that? But of course, you need to prove something about the Laplace transform of this function, not something that looks like this function. Right. So this numerically verifies the evenness and the fact that it's rapidly decreasing, and the positivity, because the zero is over here somewhere. Please interrupt me if you have any questions.
Sorry, so evenness is only numerically verified?
No. Evenness is already done in Riemann's paper. Yeah, I'm just saying that if you want to see it numerically, here's a picture.
And where is that? Where it drops to almost zero, the 0.2?
No, well, that's just visually what I said. I just said it looks, it's practically, it doesn't go. It's pretty close to 0 already at 0.4. There's nothing special about 0.4. I just picked that out because you can.
Oh, I meant the point before that, where it's with the. Just after 0.2 or whatever. So is it going?
No, I'm not sure what's special about it. Any of those points. Okay, so here's some history. So as I say, this formulation of the Riemann hypothesis already appears in Riemann's original paper. Riemann did not have this extra lambda factor. Polya was the one who introduced this perturbation. Let me go back. So we begin with this f being that particular capital phi, and little lambda equals 0. So you just have the Laplace transform. There's no extra Gaussian factor. Polya was the one who had the idea. Well, let's sort of perturb the C function by this factor, and see if that helps understand things. Actually, there are other ways one could perturb it. And there's a recent preprint of Dan Romick, who's in the audience, which kind of does different kind of perturbation or related kinds of perturbations. This was the one that Polya first did, and his idea was So here's I think I may have introduced this in the previous slide. PIZ is just an abbreviation for the purpose of this talk of pure imaginary zeros, or the pure imaginary zeros property, that all the zeros in the complex plane of this Laplace transform are pure on the imaginary axis. And Polya seemed to hope, or thought it might be possible, that even with a perturbation, no matter what sign the perturbation was, maybe the zeros were always on the imaginary axis. And of course, if that were the case, then that would include little lambda equals 0, which is the case that you're really interested in for the Riemann hypothesis. He also studied this kind of question and showed, for example, that as you vary lambda, once you have any value of lambda where you have the pure imaginary zeros property, then increasing lambda doesn't hurt that, kind of only helps it. So increasing lambda sort of helps or doesn't hurt the pure imaginary zeros property. Decreasing it could hurt it, but maybe it doesn't. So as I say, it seemed that Polya thought maybe even when you made lambda negative, even arbitrarily large and negative, maybe you also had the pure imaginary zeros property. If that were true, then that you could try to prove that more general thing, and that would give you as a corollary the Riemann hypothesis. Right. So then the next kind of major development was in a 1950 paper by a Dutch mathematician. I usually say the way it looks like in English, De Bruijn, but that's, I'm told by my Dutch friends that that's disgustingly wrong pronunciation. It should be something like Bruijn. But I'll stop trying to do it. So. Anyway, De Bruijn or Brown had a paper in 1950 which proved that even if, whether or not the Riemann hypothesis is true, which is the pure imaginary zeros property when little lambda equals 0, if you help it enough, basically by making this little lambda equal to 1/2 or bigger, then the zeros certainly are on the pure imaginary, on the imaginary axis. And that was an argument based on the fact that you already know that the zeros are in the critical strip, and it sort of is a kind of an extension of Pouillet's arguments. Not only does making lambda more positive from 0 help, or not hurt, but it actually helps. It helps enough that it squeezes the zeros which might have been off the imaginary axis but in the strip all the way onto the imaginary axis. So once you get to lambda equals 1/2, that puts everything in that strip, which is where all the zeros were, onto the pure imaginary axis. So okay. So that was a major result. So then there's a paper of mine in 1976. If I don't run out of time, I'll explain later why I was studying this. I wasn't interested at the time in the Riemann hypothesis, but interested in some statistical physics, things related to Euclidean quantum field theories, which motivated the study of some questions, and as a kind of byproduct of that, one got a result about this perturbed C function, and which turned out to be of more interest than the Euclidean field theory questions that motivated it. Anyway, the result was basically that this hope of Pouillet's was not valid. That is to say, if you make lambda, it's agnostic about the Riemann hypothesis, but it says if you make lambda sufficiently negative, then in the kind of hurting direction, at some point you will not have all pure imaginary zeros. So there exists some lambda basically sufficiently negative but still finite negative, so that you don't have the pure imaginary zeros properties. Zeros come off the real axis, off the imaginary axis eventually. So if you combine that with Pouillet's monotonicity result and De Bruijn's result about what happens when little lambda equals 1/2, it conclude that there is some kind of critical value of little lambda, which is called here capital lambda, somewhere between -infinity and 1/2, so that you have the pure imaginary zeros property. You don't have it up to lambda, but you do have it starting from capital lambda and above. Okay, this has since become known as the De Bruijn-Newman constant. And since you're really interested for the Riemann hypothesis in the case when little lambda is 0, the Riemann hypothesis can be restated as is equivalent to the statement that this number, capital lambda, is less than or equal to 0. Okay. So let me kind of restate some of these things next. So this was the result of De Bruijn, 1950, was that this constant was strictly less than or equal to 1/2. My result was really that it was strictly greater than -infinity. And then also in that paper, I conjectured that it was greater than or equal to 0. So that means that, well, if it's greater than 0, then the Riemann hypothesis is false. If it's equal to 0, the Riemann hypothesis is true, but any small perturbation by taking little lambda even slightly negative would have some non-pure imaginary zeros. So in that paper I said this conjecture was quantitative version of the statement that if the hypothesis, if it's true, is only barely so, in the sense that any small perturbation of this sort in a bad direction gets the zeros off the measuring axis. Yes.
Can you say something about the intuition that led you to make this conjecture?
Yeah. So I've been asked that a few times, and my memory is that I saw some more classic paper which said something of this sort. I mean, it wasn't about this lambda.
It's kind of a fragile.
Yeah, that it's fragile. But I tried to look back and look at some of the papers that I probably looked at, and I couldn't find the paper that. So I'm not sure there was such a paper. Whether I'm just imagining it. Yeah, so I can't, unfortunately, I can't shed a great deal of light.
But if this conjecture is true, then and if the Riemann is true, then the Poyer's idea of perturbation is not going to help.
Yeah, that's right. So I mean, this hope that you can make perturbation arbitrarily negative, that's already was disproved in my paper. But yes, but what you say is correct. Yeah, so I have a kind of complicated joke about this sort of issue, but it would take too much time. But it's you know, it's well, we'll see that shortly that because of recent developments, which I'll get to, which is about a year old, of Rogers and Tau. The Riemann hypothesis is now known to be equivalent to this constant being 0. So, so I have a personal desire that the Riemann hypothesis not be true, because if the Riemann hypothesis is true, then it's unlikely that the constant will continue to be called the Newman constant. Anyway, there's a further version of that, which is the joke part, but I'll skip it.
So your conjecture then it amplifies the Riemann hypothesis. It says that all the zeros are simple.
If the zeros were not simple, then
because
that would already
this is false. I mean,
yes.
They have to become non-simple before they.
Yes, that's correct. As you vary the little lambda, before something gets off the real axis, they have to kind of come together and yes, and then move off. That's correct. Okay, so now some of the history of this conjecture. My result was basically that it was strictly greater than minus infinity. That's not a very impressive bound, but it's something. And De Bruyn's was that it's less than or equal to 1/2. So there were improvements. And there was a whole sequence of papers starting from 88 in which actual bounds other than strictly greater than minus infinity were gotten, starting from minus 50, and then improving. I'm skipping most of them, improving to a fairly small negative number, and then even smaller over here. And then more recently, there's been a further much better lower bound, which we'll get to in a second. And the only improvement of the upper bound was, instead of less than or equal to 1/2, was strictly less than 1/2. That's a paper of about 10 years ago of He, Kim, and Lee. This doesn't look like much of an improvement, but it's actually is much more significant than it looks like, because there are other things in that paper that are quite useful. So maybe I'll get to mention. So as far as the lower bound, this sequence of improvements was all consistent with the conjecture. This conjecture that it's greater than or equal to 0 was, but obviously didn't prove it. But that has been changed recently. I mean, not so recently, a year ago, a little over a year ago. So there's a paper of Brad Rogers and Terry Tau in which they actually prove that conjecture, and the basis of roughly speaking, the basis of the proof is all these improvements were based on, so as Elliot said, in order for things to move off the real axis, basically zeros on the imaginary axis have to come together in a pair and then move off in a pair off the imaginary axis. And so if there's a pair of zeros on the imaginary axis but very close together, it shouldn't take much to perturb them to come together and move off. And so the lower bounds were gotten by looking at very close pairs of zeros near each other on the imaginary axis, way up on the imaginary axis somewhere. But what Rogers and Tao did was kind of do a more robust version of that argument, in which you didn't look at single pairs of zeros, but at kind of distribution of the spacings of the zeros. And so, but it was it used some of those ideas and other ones, back from these specific bounds, and they studied the motions of these zeros as you vary this parameter lambda, which you now think of as a kind of a time, and this equation is actually satisfying a backwards heat equation in the parameter t or lambda, and you can study that, and then also the argument is sort of, roughly speaking, that if the capital lambda were negative, then you already, for that negative value of t, you would already have zeros on the imaginary axis, and now you move t from the small negative value towards 0, and that would give you a certain motion of those zeros, which would tend to make the spacings get more separated. They kind of repel each other, the zeros. To write down the system of ODEs that the zeros satisfy, they kind of repel each other, and so the spacings would get more regular, and it would get regular enough that by the time you got to t equals 0, spacings would be sufficiently regular that they would violate known results about the distribution of the spacings of the actual zeta function zeros, assuming the Riemann hypothesis, which you're allowed to assume in the context of this proof. Okay, so that's about, the upper bound. The lower bound has now been improved. Well, I shouldn't say as much as possible. Perhaps somebody will prove that it's strictly greater than 0.143 times 10 to the minus 15th, which will disprove the Riemann hypothesis. But short of a disproof of the Riemann hypothesis, that's about as you can't do any better than with the lower bound. The upper bound, though, remember that the Riemann hypothesis is actually equivalent to the lambda being less than or equal to 0. Of course, now we know it can't be less than 0, so now it's equivalent to lambda being equal to 0. And so, in principle, if you did a sequence of upper bounds which improved the 1/2 going down to 0, that would prove the Riemann hypothesis. So you would have heard it if that had happened. But it has been, or it is being improved. So there's one of these polymath projects, number 15, which you can look up, 11 threads about it online, has been working on improving the lower bound better than 1/2. So basically, it's gotten as far as getting an upper bound improving from 1/2, and it's apparently down to 0.22. It says here as of October 2018, which gives you a hint when these slides were prepared. But it actually is still the same. The possibility of getting down to 0.11 is it would require, this stuff uses all kinds of machinery, including very substantial numerical computations, but which can be made rigorous. But you would need even more numerical computations, which would be of the sort of verifying that the zeros up to even farther than people have gotten along the imaginary axis, going up, are still on the imaginary axis. And if that were done enough, you could possibly get down to 0.11. That's what seems to be the case. It does not seem likely. It does not seem likely that this kind of argument without some extra new ingredient will lead to a proof of the Riemann hypothesis. from my point of view, that's because it's not using Ising models and Lee-Young theorems. Unfortunately, I don't know how to do it that way either. But anyway, so one comment is that these improved upper bounds are using the Key, Kim, and Lee results, not just that they strictly less than 1/2, but they had another result, for example, that when you make the little lambda positive, even very small and positive, you already know that there are only finitely many zeros off the imaginary axis. So that piece of information is very useful in getting these improved upper bounds. Okay, so I have 15 minutes. That's not right. Can I be my own timer? Okay, so I do have some time to talk about the mathematical physics or statistical physics background, and it's related to the theorem of Lee and Yang. We've heard this discussed in several lectures. From the point of view of this talk, the two comments. One is that by taking an Ising model of the sort that the Lee and Yang theorem applies to, and then taking positive linear combinations of the Ising spin variables, that gives you a random variable whose moment generating function, which is this, with the first lambda equals 0, is the partition function for that Ising model, the Lee-Yang theorem is often correctly described as the circle theorem, but that's about zeros on the unit circle. Here they're on the imaginary axis because there's a change of variables, and basically looking at e to the points on the circle e to the points on the imaginary axis are the points on the unit circle. So it's a simple change of variables. Depends on whether you think of the Ising model as a model of a lattice gas or a model of plus or minus 1 variables. And anyway, so it gives you random variables whose distribution, probability distribution rho, has a moment generating function, which is this thing with little lambda equals 0, which has the pure imaginary 0 property. And that's very useful, as Elliot Lieb discussed, very useful in statistical physics. That's why Lee and Yang were interested in it. And it's also useful for a related subject, which is called Euclidean field theory or Euclidean quantum field theory. In that related subject, you want to study variables which are not just values plus or minus 1, but take real values. And so you replace the measure, which is the sum of 2 point masses at plus 1 and minus 1, by some measure with a density, e to the minus v, of various forms. And then it's very useful to have a Lee and Yang type result for those kinds of models. So those are lattice Euclidean field theories. It's particularly useful because of it's somehow natural within that setting to put in this Polya kind of factor, where you put in the e to the lambda u squared, or here it's now changed to e to the minus b u squared. And if you can put in if the Polya idea, which isn't the case for the capital phi, if it were the case for this function, that you could put in a little lambda with any sign, that would be very useful in the Euclidean field theory context, because it would allow you to put in what would be called a mass term with arbitrary choice of the mass, and that would be very nice. So for the purposes of this talk, it's a bad choice of language, but anyway, I'm calling such a function f of the form e to the minus v perfect if you can perturb it even in the bad direction, even with a negative lambda, and still have the pure imaginary zeros property. Well, there are examples of such things. Well, of course, the Ising case, where it's not a function but is a sum of 2 point masses, of course, is fine, because if you multiply by e to the minus bu squared, it doesn't change anything except the normalization. But there are other examples where it's known, and here's the most well-known one. It's where the function v is a fourth degree, even fourth degree polynomial. So it looks like this, and you can put in arbitrary lambda or an arbitrary b, positive or negative, and you still have this pure imaginary zeros property. So in the quantum field theory context, that was a result of discovered by Simon and Griffiths. It actually was already known by Polya in the 1920s, because he studied things with Fourier transforms, which are only pure imaginary zeros. Of course, Polya's result wouldn't be quite enough in the Euclidean field theory context, because you need a multivariate version of it rather than a single variable version, which you get from the Simon-Griffiths result. But anyway, that's an example. So what motivated me in that 76 paper was I wondered whether there were other things besides the fourth degree polynomial. So one is if you want an even function, and sort of an exponential interaction would be something like a hyperbolic cosine. So I was interested whether that thing was perfect in this language. So an exponential or hyperbolic cosine field theory, would you have a Lee-Yang type result for arbitrary little lambda or arbitrary little b? That's what I was set out to, so I was kind of hoping that would be the case. In the process of studying that, in fact, I basically characterized all perfect Fs. And that class of Fs, which I won't get to it, but in a later slide I actually write down what that class is, it did not include this one that was started out being interest. So that was a negative result about a certain quantum field theory model. On the other hand, it also did not include the capital phi of the Riemann hypothesis. Well, that's also a negative result in the sense that Polya's hope is wrong, but that's sort of interesting in the number theory setting, it seems. And so the paper I wrote was about that side of things, and that was the result that showed that this capital lambda was greater than minus infinity, and therefore was a well-defined constant. So that's the history of somehow how the statistical physics Lee-Yang type thing kind of motivated that paper. So now in the few minutes remaining, I wanted to mention a few more recent things. And these are discussed in much more detail, obviously, in this review paper, this quite recent review paper here. Oops. So here's an example of a result. So one often comes up with functions little f or measures d rho, and you want to know whether you have a Lee-Yang type property or a pure imaginary zeros type property or not. And here's an example of a negative result, fairly general. So here's a case where unlike in the Riemann hypothesis case, where the rho that you're interested in has density capital phi, which is very rapidly decreasing, suppose you have something which is not rapidly decreasing at all. It's so non-rapidly decreasing that it cannot, if you put in a Gaussian factor with lambda positive, it will no longer be integrable. So, for example, I don't know, a symmetrized exponential distribution goes to 0, like e to the minus absolute u, or something even slower, constant over a Cauchy distribution, or constant over 1 plus u squared to the 12th power. So if you put in a positive lambda, it's no longer integrable. Then the theorem is that now if you put in a negative lambda, of course, it will be have a nice Gaussian tail. And you can ask, is the moment generating function or Laplace transform have this pure imaginary zeros property? And the answer is no. For every positive for every negative lambda, even though the moment generating function or Laplace transform is now a nice entire function, it does not have only pure imaginary zeros. So that's a somewhat interesting negative result. But the proof of it is I find more interesting, and it's based on what I still think is somewhat surprising result about convergence of probability measures, which I'll state in a moment. I won't talk about this connection, both because it goes in a different direction because I don't remember it very clearly. But here's the convergence result. So it ties together the pure imaginary zeros property of moment generating functions and weak convergence of probability measures in a somewhat unexpected way. So here's the theorem. So I define a class of random variables. It's really a class of their probability distributions. So the random variables are even, so the probability distribution is symmetric with respect to reflection about the origin. It has at least Gaussian tail fall off, so you can, unlike the example I was talking about before, so that you can multiply by an exponential with a small positive b, at least for small positive b, and still get something integrable. And it has this pure imaginary zeros property of its moment generating function. That's this class. The theorem is that if you have a sequence of such variables, and importantly, you make no assumption about uniformity of what b you can put in there. So the b could be getting very small as n gets large. So even though you have a Gaussian tail, the tail could get getting weaker, worse and worse. And if you have a limit in distribution, which is a very weak kind of limit in probability measures, it just says the Fourier transform converges pointwise on the real line. Normally, that's not enough to even know that the limiting variable has a second moment, for example. But in this case, somehow the pure imaginary zeros property tells you that just knowing weak convergence, even though there's no uniformity at all in this b as a thing on n, the limiting variable is in this class, and in particular has to have at least Gaussian fall off. So there's something mysterious about that. I mean, it's less mysterious than it first looks, because somehow, even though you don't assume that b is uniform, the pure imaginary zeros property implies at the end that it is uniform, or else you couldn't have the weak convergence.
So it's a kind of like a version of a Gurwitz theorem with H, not with G.
If you say so.
About convergence of analytic functions to non-zero.
Oh, Howitz. Well, no. So if you made the assumption that this b of xn was uniform, then it would follow from.
Yeah, but they say it's kind of version.
Yeah, it's somehow where you get the uniformity seemingly for free.
Yeah.
Of course, it's not for free because you have to know about where the zeros are.
And what? But do you get? So you get uniformity in the
Yes.
And what is that? What is that engine for that? You can say in a few words.
I can say in a few words, and then I guess I will stop since. Okay, actually, let me go to a formula. Oh, wait, sorry. So the key is as has come up before in other talks, the key is once you know about the zeros, then you can write a Hadamard factorization for this moment generating function, a product over the zeros, and it looks like this, where you put the zeros in, they come in pairs, as you combine the two pairs. And furthermore, the second moment, this is a moment generating function. The second moment is the second Taylor coefficient, and that's related to the b appearing here and these zeros, plus or minus I, y, k are the zeros, by this formula. So the proof is sort of in two parts. One is that if you make a much weaker assumption than uniformity of the b's, just that the second moments are uniformly bounded, then because of this identity, that tells you something about the zeros. And so that's enough to get much more uniformity than you thought. The second step is that just the weak convergent is enough to show, again using this identity, but now replacing z by it, so you're looking at the Fourier transform, is enough to show that you couldn't get even, because of this formula, you couldn't get even the convergence and distribution of the Fourier transform on the real axis without having a uniform bound on the second moments. And so it's kind of in two steps. Okay, so yeah, that's it. Thank you.
Any questions?
So I guess De Bruyn's De Bruyn's proof was based on this operator e to the negative lambda d squared. It shrinks the size of the string.
Yes, yes.
And he produced a lot of other operators doing that too.
Well,
so can you? It's natural to look at other types. So you may look at this as a flow, right?
Yes.
In lambda, and you can. There's a lot of similar flows there.
Yeah, so I think that's exactly the point of view in Dan Romick's recent preprint, looking at other flows. Is that right?
But
yes, I mean,
that's multipliers, and you sort of shift the windows.
Yeah, yes. So anyway, I basically agree with that. I don't think there has been too much work of that sort, and of course, a priori, it's unclear. You know, could be useful, but yeah, yes.
Yeah. But the flows that I have don't have this monotonicity property.
Okay.
Unfortunately, but they have other nice properties, so it might be interesting.
Does the derivative of the zeta function have any interesting or supposedly interesting property? I mean, we're talking about zeros on the imaginary axis. What if I look at the derivative? Well, the derivative with respect to lambda, for example. Do I see am I expected to see anything interesting? It's a wild question, so you can give a wild answer.
Yeah. Yes. But I don't know what it is. Yeah. As I say, the Rogers and Tau paper, studies that motion which is a backwards heat equation, and so derivatives obviously come up. Something which is a recent part of that, this is going off in a somewhat different direction, a recent part of that Polymath 15 is that they've been studying numerically what happens when you, instead of, if you take the lambda to be, say, large and negative, now you're off the real axis, the zeros, many of them, some are still there, and they study the locations of them, and they seem to come in very interesting patterns which they're trying to understand. It's not clear what, one comment was that, that might lead to some proof of the result of Rogers and Tao proved that old conjecture. But that's going off in a different direction. But anyway, I think things like that should be interesting. But
so I have a question. So is there any sort of related development if you were to look at the generalized Riemann with various characters?
So roughly speaking, I'm the wrong person to ask that question to, since I'm pretty ignorant about analytic number theory. But I have seen papers that have to do with generalizations of my conjecture to other zeta functions, some of which have been proved, I think, some of which have been disproved. So that Jim, did you have it?
Yeah, but Dan can go first.
So I just wanted to make a comment. There's this other recent paper by Ken Ono, Zagier, Roland, and Griffin. I think it's mentioned in your survey as well, which follows up on another approach of polia, of what's called the Jensen polynomials, Do you want to say something about that? I mean,
I think you better say something.
I don't know that much about it.
Yeah, more than me.
But, it's just something I think might interest people here. But it's very recent. It's like from a few months ago or something. So it's on the archive.
Yeah. So I have a different comment, which may or may not be related to what Jim may or may not ask. But I sort of alluded to this before. I talked about the Li and Yang result, and also to the topic of one of the topics of this workshop. I talked about the Li and Yang result. That was a kind of motivation for the paper I did, but it wasn't really about that. It was as I said, the Li and Yang theorem gives you a mechanism for generating random variables or their distributions, probability measures on the real line, which have this pure imaginary zeros property of their moment generating function or Laplace transform. It is, potentially the Riemann hypothesis could be proved if one could find some sequence of Ising models and such, linear combinations of the spin variables, positive linear combinations of the spin variables, and then limits of those things, where in the limit you would get exactly the distribution whose density is proportional to the function, that particular function phi. So nobody knows how to do that. So the Li-Yang theorem is potentially sort of sitting there as a machine that could give the last step in the proof, but the first step or steps, is the hard part. Finding the right Ising model or sequence of Ising models that would give you that particular capital phi. On the other hand, if you go to that old review paper of Newman and Yor, you will find that something that was known somewhat before then, that somewhat funny-looking capital phi arises in natural ways from other probabilistic settings, like Brownian motion or Brownian excursions. Unfortunately, there is, I think I wrote that down, that doesn't seem to be any relation between those Brownian motion way of getting the function phi and Ising models. If there were, maybe you could put together the two things and kind of do something. But so that the Ising models give you a way to show the right property of the zeros of generating functions. Brownian motions or Brownian excursions give you a way of generating the right phi. So each of these things has kind of half of an argument, and it doesn't seem to be, so far, any relation between those two things so that you combine the two halves. So that would be, you know, a good exercise for this workshop. Yes.
Yeah, so in that vein, am I right? In the Ising context, the symmetry or the evenness of rho is somehow obvious a priori because it's just sign flips?
Yes, that's exactly correct. So the random variables one's looking at are positive linear combinations of the spin variables. It's in an Ising model where you have pair ferromagnetic interactions in the Gibbs distributions, but no magnetic field except that you know, that's kind of hiding in the moment generating function. The variable is the magnetic field, but absolutely correct. So you're doing the Ising model in which the random variable you're looking at is a sum of spin variables that is symmetric under flipping all the spins because you don't have the magnetic field term, the linear term in the Ising Hamiltonian. So it's manifestly symmetric distribution. This distribution phi is even, but it's not manifestly even. That takes an argument. And similarly, the thing that comes up from Brownian motion or Brownian excursion, once you take out the right factors, turns out to be even, but is not manifestly even. And so that mystery of sort of where the evenness comes from in that case, you know, maybe if you figured out some hidden relation with Ising models, that would answer that question along with the Riemann hypothesis. Of course, you wouldn't be so interested in that. I mean, that would be a minor point. Yes, but that's right. This is manifestly even. Yeah, I should.
That's somehow the big problem, or a big problem in trying to bring Ising to the Brownian stuff. In some way, in my opinion, the Brownian developments contribute nothing to helping the Riemann hypothesis. Right? I mean, if
not so far.
No, but I mean, it's almost clear that they can't, right? Because in the end, you don't get anything more than you know, a random variable that has this density. And you don't get any analytic handle on it besides what you already have from the number theoretic setting and knowing the Pottier theory and so on. Nobody's yet ever, or to my knowledge, been able to prove anything sort of interesting about these functions that wasn't already known. Right? It's just, oh, these functions are the probability densities of certain random variables, which are very appealing and nice to think about, but the transfer of information is all in the direction of known facts about this phi function imply rather extraordinary facts about Brownian excursions.
But Tao used hit equation, which is kind of related.
Yeah, which is not so far from Brownian motion.
Yes,
that's right.
yeah.
So I mean, as soon as you've got that e to the minus something z squared, you know, you're in a Gaussian world and you want to do something. Yeah.
Any other questions? Any solution? That's even better. Thank you very much. We can